Yeah, hi everyone. I'm Sushmita. Now I'm going to present you the transformer architecture here. This is a transformer architecture. So this is a transformer diagram which contains encoders and decoders. So uh, first let me tell you like what is a transformer, what is a use of the transformers. What they are specially designed for and what is the main use of it. So we'll discuss it now. What is a transformer architecture? At first, to know the transformer architecture, we need to learn like some questions like what is a transformer, what is the use of the transformers, and why we are using these transformers. So I'll explain you here. A transformer is a deep learning model and is mainly used for natural language processing tasks. So, it is a deep learning model. It was introduced in 2017 in the paper Attention is All You Need. So, why it is made? So, it is mainly designed for the sequential tasks like sequence to sequence tasks such as translation. So, here translation like from one language to the another language like from I have a sentence in Telugu, so I need to translate it into English. I need to translate that into Hindi. I need to translate it into French. So for this translation we are using the transformer. And then for chatbots, for text summarization, and for text question answering. So, for these tasks only, the transformer was specially designed here. So, why? Why transformers were needed? So, earlier we have some neural networks out there. Those are like recurrent neural networks and LSTMs out there. So, what is the problem with RNN and LSTMs means? So, like transformers did not processes data sequentially like what RNNs were do like uh, it reads the text one by one. Like if we have a sentence with a we have a sentence, so it the sentence contains a number of words are there. So what RNN will do here is it reads text one word at a time. So, if it reads only one word at a time, it will be very slow, right? And then if we have a long sentence, by the time we reach to the last word in the sentence, it will forget the before one. So it also has a problem like forgetting the long sentences also. So that's why the transformers coming to the picture. Transformers are like it does not process the data sequentially, so it will completely dependent on the attention mechanism. So it has an parallel processing, like it will read all the words in the sentence at a time here. So that's why it has a faster training also. So this is the use of it. So for data parallel processing also we are using these transformers. So here, yes, why transformers were needed, the problems with RNN and LSTMs, and the sequential processing. So for RNNS, it has a problem like sequential processing. So it has a slow training and long-term dependency problems. So as I said, uh, if we have a long sentence, by the reach of the end of the word in the sentence, it will forget all the before data and difficult to parallelize, like it will read only one sentence or one word at a time and struggles with long sentences. So these are all the drawbacks. That's why with neural networks, that's why we are using the transformers here. And this is a transformer solution. Like it uses self attention, as I said, it uses self attention instead of recurrence. And then it process entire sentence at once. Like it will read all the words in a sentence at a time, not just by word to word. And so, whenever it reads all the words at a time, so it is more faster and more accurate also. So it won't forget the previous words also. So it can handle long range dependencies well. So this is the architecture, and why we are using this architecture of transformers. So coming to the transformer architecture. So this is a transformer architecture. So the transformer has two main blocks. Those are encoder and decoder. So at first, what we will do here is in this architecture, at first we'll take an input like the sentence, a sentence we will take, and then we'll do the encoder for that input, and then we'll do the decoder. So then we'll get the output. So yes, yeah, we have taken this input and we are doing this encoder, decoder, and we are getting or generating the output. So what is this encoder and what is this decoder here? So in just simply encoder is like understanding the input sentence. Whatever the sentence we are giving to the input, the encoder will understand it. Like what is this? Uh, what is that word, what is the sentence they have given, it will understand the sequences, and it will answers like uh, who is related to whom, and here which words are matter more. So this is how the encoder will read the and understands the input sentence what we have given. And then decoder, what it will do means it will take the input whatever we have given and then understands the input and then generates the output sentence here, like based on the input we have given, it creates like text one word at a time here. Like for example, I have taken the input here, like I love machine learning. So, as I said before, transformers were designed for translation also. So, here, translation, we are doing the translation. Like we have taken the sentence in English and then we are translating it to the French. So, decoder, what it will do? It will generate the output based on the input we have given. So, this is a encoder and this is a decoder. So, transformer specially designed for tasks like translation, summarization, question and answering. And in this architecture, we have an encoder and we have a decoder. So encoder is for understanding the text and decoder is for uh, like generate the output. So what is the main idea of these transformers? So the main core idea of these transformers is like to replace the RNN with the self attention. So mainly the transformer goal is to uh, use this self attention, like, and then it has to do efficiently like long range dependencies, and it has to process all the tokens at the same time also, and should work for large data sets by not forgetting the previous words. So here, as I said, transformers completely wants to use the self attention. So here, what is a self attention? Self attention means we have a sentence. So every word in that sentence looks at every other word and decides what matters. Like every word. in a sentence we have a number of words are there, so each word, every word looks at every other word and then decides like which word is important for me, which words are important. So this is called the self attention. Yeah. So as I have said the I said what is a just a simple definition. So here we have an example for this. The animal did not cross the road because it was tired. So this is a sentence we have given. And what is our question is what is it? Here this is the it. So what it refers to? What is this it? It means here animal, or it means here road, or it means tired. What? What? We don't know, right? So here question what is it? What this transformer will do here is it will looks at all words. So for to know this it will look every other word like the animal did not cross, and it will look at all words and assigns important scores, like it will assign some important scores for each word, and then it will learns like it for animal, not a road. So each word asks like which should I pay attention to. So self attention means each word can look into the another word to know which word is important, right? So yes, how it looks at other words. So how does a word look at other words? Here computers can't look. As we know, they use only numbers here. So here what it will do is it will take each word from the sentence and it will convert that word into a vector here like a number numerical format. So from each word vector we have a three versions. So we have a sentence like, so this is a sentence, suppose this is a sentence, and we need to find the, we have a query here and we need to check it every other word. So computer don't understand the words, so that's why each word will become a vector like the will convert into a number, animal will convert into a number, did not, so every word will convert into a number. So number, like number means a vector. So for each vector like for every, so this is a vector, for every vector we have a three aspects. Those are like it may be a query, it may be a key value, it may be a key, it may be a value. So from each word vector we create three versions like query. Query means, as we all know, question like what I'm searching for. Key value. Key means like what it is offering, like what it has a matching values, what it has the relevant words are there. And this is a value means actual information what we have. So like as I said, what is self attention? Self attention means every word will look at the other word which is a more important for that word. So how it will look? It will convert all the words into the vector and then it have a query key value also. And then yes, we said self attention is completed. And then how we can calculate this attention? So this is a formula to find the to calculate the attention. So attention of q comma k comma v equals to softmax of q into k power t. So here what we are doing means this is a dot product. Like we have a query, as I said before, it is a query. So to find which words are relevant to this query, we need to do the similarity search. So for this, we are doing the dot product for this query and the key value. And then here we are doing the scaling, and then we are applying the softmax. Softmax means like to convert all the scores into the percentages, and then we are multiplying with the final output, like uh, the value, and then we'll get the final output as an attention. So this is a formula to calculate the attention here. So yeah, this is a formula to calculate the attention. So here it is in the theoretical format, attention calculation. So how we calculate the attention here, like for each word we can compare the query with all the keys we have, and then we'll get the similarity scores. Like this is the similarity score, q into k power t, and then we are converting scores to the percentages. So as I said, we are using the softmax, which is used to convert the uh, scores into the percentages, and then we'll use these percentages to mix the values. So as a result, a word representation that includes context, like we know, suppose we have two examples out there. One is a bank which is related to money, and one is a bank which is related to river, so that we can find those are two bank words are different. So this is how we can calculate the attention, and we can get the word representation here. So uh, we know self attention. Then what is a multi-head attention? So what is multi-head attention? Why we are using this multi-head attention? So humans don't focus on only one thing. Like yes, we are the humans. We could not focus on only one thing, right? We can we can think many things at a time, and we are focusing many things at a time. So this, so we can look at, so suppose if we take a sentence, what humans will do here is they can know they'll look at the meaning of the sentence and the grammar of the sentence and the position of the sentence and the relationship of that sentence, like which word is related to with which word is related to whom. So a normal human will look at all these things. So same as like humans, transformers also does the same. So multiple attention heads means each head learns something different, they combines all of them. So as a human, transformers also will look at all these things in the sentence here. So this is a multi-head attention. Multi-head attention means everything. It may be a human or it may be a transformer. Everyone will look or will focus more than a uh, single thing. Like they don't focus on only one thing. They at a time they look at more things. So this is about giving the order for each words. So we have a this is a sentence, we have dog bites man, and then we also can get a man bites dogs, right? So same words but different meaning. So how these transformers will handle this? So the input what we have given is dog bites man. So what it will returning as like man bites dog. So we don't want this, right? We just want only dog bites man. So for this we need to give order for each word. Like we need to give an order for this word, and we need to give an order for the second word, and we need to give an order for the third word also. So to give like giving an order for each word is known as positional encoding here. So here we add positional information to word vectors, so the model knows first word, second word, or so this is a sentence. So for first word we can I can give like position 1, position 2, position 3. So for each word giving a position is known as a positional encoding. So how can I calculate this positional encoding means? So at first what will happen here is, at first we'll take a sentence. Sentence is a combination of words. So all the words, uh, like all the sentence what we have, it will be tokenized by using the token, like each word. So D is a token, quick is a token, brown is a token, fox is a token. So these are all the tokens. It will divide it into the tokens, and then all these tokens will converted into the embeddings. Why? Because computer won't understand this text. So these are the embeddings for each token. These are all the token embeddings. And then we are assigning the position for each word. So here we are assigning 0 for this word, 1, 2, 3. These are all the positions what we have given in. So here we are calculating this. So every vector has a dimensions, like 512 dimensions. So we have a different dimensions. If we take a even dimensions, we have to use this one, or by using the sign we can find this. And if we have a odd number of dimensions, we have to use this cos function here. So here we'll get, by using this functions we can get to know the position of the word. And then uh, we are adding this, the embeddings plus positional encoding. So by using these two we can get the final output. So yes, transformer architecture means, we have discussed what is a transformer, what is the use of transformer, why they are designed, what it contains, like self attention, multi-head attention, and what is a Q, K, V. So we all discussed it. And then we are going to get to know the encoder and decoder. So this is the encoder and this is a decoder. So here, encoder and decoder. As I said before, encoder is just reads input and understands the meaning of the sentence. And then decoder means it generates the output, like, and it will predict the next word step by step. So this is an example. Encoder example means understand the sentence. Decoder means it will generate us the responses. This is a simple definition for the encoder and decoder. So before we are going to the encoder and decoder, we just want to learn, like, some basic fundamentals we have, like to know some, what is an word, what is an embeddings, and what is a word to vectors, and what is a positional encoding, what is a attention ingredients like a query, key, value, and what is a similarity and relevance, how the tokens influences the output. So we need to know all these fundamentals here. So first, word to numbers. So what it will do here is, um, as we know, computers cannot understand these words. All the words can convert it into the numerical format. So this is called the embedding. Embedding means converting the words into the numerical format so that computer can understand. So learn words meaning from context, words used in the similar context, similar vectors. So what it will means, a words can convert into the numbers. This is called the word to vector. Vector means embeddings. So by using these vectors, whatever the query we have asked, that will be based on this embedding only, we'll get the responses here. and it will so the computer know by using this number, like if we have a 0.21, so that it could know like what is the word, like if we see a word we can understand it like it's just a cat. So the computer don't understand, right? So it will use that number, by seeing that number it can know that it is a cat. So yes, it learns word meaning from context. By using these numbers it can learn that what is that word meaning, and words used in similar context or like similar vectors. So for example, I have taken the king. So if I want to know the queen, we have to do this king minus man plus word. So it will create all the embeddings for these words. So transformers do not use word to vectors directly, but it will get to know the embeddings and then know the meaning, and it will generate us the responses. So positional encoding means so the transformers don't know the order. So for example, I have taken a sentence I love AI, and it will written as like AI love I. So it's not right, right? So these are the similar words, same words, uh but these two have same embeddings? No, it won't have a same embeddings. So it will return as the wrong input, right? Wrong output, right? So, to do this, for this we need to add the position information. So this is the first number, this is the second number, and this is the third number. Based on that number only, it will produce the correct output. So we add the positional information. So at first we'll take the input and then we'll do the embeddings, and then we are adding the positional encoding here. Then we'll get the final output. So, as I said before, sine and cosine functions, these are all used to learn the relative distance between word to word. So, it generalizes to longer sentences like token 1. So, this is a token 1, this is a token 2, this is a token 3. So, you don't know the order. Positional encoding will do what? Like, knows it is a first. This is a first token, this is a second token, and this is a third token. This is how it will work. Without positional encoding, transformer is blind to word order. It will return as like a jumbled sentences. If we give the positional encoding to each, like if we give the a number to the each word, it will return as the correct output. So what is this QKV? So here, as I said before, each token has a three vectors. One is query, key, value. Query means what I'm looking for, like the query what we have. So we have a document and I have a query. Within that document, I need to get the answer for my query. So this is how the query, what I'm looking for. And key, what do I offer? So for my question, what it has the, like, it has, it should have some matching answer for my question, right? So this is the top matching values, uh, what it has for my question. And we value, this is the actual information, and then all come from the same input embedding using the different weighted matrices. So for each query key value will do some like will give the matrices, weight matrices here. So this is a embedding into this is a weightage. We are giving the weight matrices for each query, each token. And then we have a similarity and relevance, like so we have, suppose we have a sentence like the animal did not cross the road because it was tired. So what is it refers to? It may be the animal or the road, or it was tired. So we'll have a step by step attention here. So we need to know the what is it. So we have taken the query of it, and then it will, we have a query. We'll compare it with the all other keys, and then we'll do the similarity search like dot product for this query and the keys, and then we'll get to know the what are the more relevant answers, like higher score to our question. Then we'll convert that scores into the probabilities, so that we can get to know the attention weights of this each word. So here we got the attention weights, like for animal I got 0.65. So for each word I have got the attention weights here. So final representation of it. So for this I'm multiplying this value of I'm multiplying the value with the weighted matrices here. This is how the token relevance affects meaning. So this is for our query, which one is more relevant here? 0.65 is more relevant, so that it refers to the animal, and tired is slightly, and the road is barely related. So in just a simple, to know the similarity, we need similarity and relevance, we need to compare the query with all the keys, and we need to do the dot product to find the relevant score, and we need to convert that score into the probabilities, and we have to find the attention weights, and then we have to multiply those attention weights with the value what we have, then we'll get the relevant answer. And then how this affects generated text. So whenever the text is generating tokens with higher attention weight, it influences the next word prediction more. Like we have a prompt like the capital of Francis. So it has a high relevance word. What we have high relevance word, next token is likely Paris. So it can get to know the next word is Paris. Why? Because it has a most relevant word. This is a most relevant word to our query. And then sequence to sequence tasks. This is like input sequence, output sequence. Like we have encoder architecture and we have decoder architecture. So and then also we have also encoder decoder combination also exists. So what is this use of this encoder decoder exists? So we have an input and we have an output. This is a sequence to sequence task. For example, translation, summarization, question answering, as I said before. So I have a problem like the input length is different and the output lengths are different. If the complete output is dependent on previous input, we need this encoder here. So output depends on entire input. Then we need this encoder decoder architecture. Whenever the output is dependent on the completely input, then encoder decoder exists. So encoder only transformer. So what is this encoder only transformer means? These are the models that use only the encoder part of the transformer architecture. They are designed to understand the text, not generate the text. So this is the encoder architecture. So what is the main goal of this is it's just understand the sequences, like who is related to whom, and which words are matter. So this is how. So these are used to design to understand the text only. It won't generate the text. The generating part is decoder. The encoder is only transformer architecture is only just understanding the text. For example, Bert, Robert, Distilbert, Albert. So we know encoder part is just to understand the text, what they are used for. Encoder only models are best at understanding tasks. As I said, this is just for understanding purpose. This is a text classification, like whether it is a spam or not. This is a sentimental analysis. It may be a positive or negative. If it is a named entity recognition, what is the name, what is the place, what is the company. If it comes to the question answering, like finding answers in the text. If it comes to the semantic similarity, like meaning comparison, words to word meaning comparison. So to understand which is related to what and what is this, these are all comes under the encoder only transformer. So yes, and we know the what is encoder architecture also. So how it will work, what happens and how it will work. So the encoder architecture working flow is the internal working means at first it will take the input processing. So how it will work means it will take the input from the user, and then input is like a big sentences, and then it will create an embeddings for that input, like it will first tokenize the sentences, it will create some tokens, for that tokens it will create some embeddings, and then it will add the positional encoding for that embeddings, like for each token it will assign the positions as I said before, and this is our embeddings and this is a positional encoding for the tokens. So by using this, uh, here what it will do is here it will do like multi-head attention also, like so as I said, step one is tokenizer. This is a sentences. This is it will tokenize these all the sentences. It will become like this is a token, I is a token, love is a token, machine is a token, learning is a token, and then it will create an embeddings for this is a for tokens it will create an embedding, this is known as a token embedding. For positional information it will create an embedding, or to know the order it is known as a positional embedding. For sentences it will give the embedding, this is known as a segment embedding. So final output is it will take the tokens and the positions and the segments, then we'll get to know the input, final input. So it has a bidirectional self attention. So as I said, self-attention means each word will look at the another word. Here bidirectional means suppose we have a word. It will look every other word, previous words also. It will look for another word also to predict the output. So here encoder out only transformers use bidirectional self-attention means each word looks at both left and right context. For example, so here we have an example. I went to the bank to deposit money, and this is another example, another sentence. I sat on the bank of the river. So here bank comes to which one? Whether it may be money or it may be referring to the river, we don't know, right? So if it is a deposit, this is a financial bank. If it refers to the river, then it is a river bank. This is why Bert understands meaning deeply. So what it will do here is uh, it will understand whether it is related to so based on this input I am telling you, uh, whether it may be a financial bank or it may be a river bank, it will understand the meaning clearly. And then same, it will check for same mechanism as encoder in full transformer. From each token, we'll get to know the weights for each query, key, value, and then multi-head attention. Multi-head attention means it allows model to focus only different types of relationships at the same time. As I said before, it will focus many things at a time. Some heads learn like syntax, semantics, co-reference, and the long-range dependencies. This is a stacked encoder layer. It usually uses the 12 or 24 bit. Here, each layer refines understanding. For in it has a usually it has a 6 layers. So for each layer, it refines the understanding. For going to the next layer, it have a better understanding. And this is a masked language modeling. And encoder only models are trained by hiding some words, asking the model to predict them. Like, suppose we have an example here. I love mask learning. So model, it predicts like machine, like what this is a mask. We don't know anything here. So this model will predicts like it is a machine. Why this works means it forces understanding of full context. It uses the before words and it will use the next previous words and next words. It will get to know the it will predict the word output. And then if you want to predict the next sentences, suppose we have the model is trained to understand the sentence relationship. For example, I went home, I slept. So what it will understand, like I went home for slept. This is how it will understand. And what does the model output? Encoder only model output means what it will return as, like it will return as a vector per token, and it will return as a special tokens also. Those are used for classification. So what is this special CLS means? Sentence meaning. It will give us the sentence meaning. And how tasks are done, like classification, question answering, and the similarity, like comparing those embeddings and giving us the similarity score. And this is a decoder only architecture. So encoder architecture is just understanding the text. Decoder architecture is to generate the output. So here a decoder only transformer is a model that uses only the decoder part of the transformer architecture. So this is designed to generate the text one token at a time. So what it will do is a decoder creates text one word at a time. So especially this is just used for the translations, like Telugu to Hindi, English to Hindi, English to Telugu, or it to maybe any language. And these are all the examples for this decoder only architecture. What they are used for, like text generation task, like text generation, chatbots, code generation, summarizing, reasoning. For all these cases also we are using this decoder only architecture here. And then if the goal is to predict the next word based on the previous words, we don't need an encoder. The decoder alone is enough. So, what is the main goal of this decoder is, suppose we have a incomplete word, just if you a small sentence. If I want to predict the next word in a sentence, uh, we just want to predict the if we want to predict the next word, we need to take the previous words. We should not take the future word. Like if we have a three words, word one, word two, word three. So if I want to predict the word four. So if I want to predict the word four, I don't want to use this word four. I want to use only a word one and word two. By using this word one, word two, we can predict the word four. So the main core idea is like a next token prediction. So everything GPT does comes from predict the next token given all previous tokens. So by using these previous tokens, we want to predict the next token here. And then auto regressive generation, like GPT generates text one token at a time. So it will return as, suppose we have a word and we need to translate it into the another language. So at a time it will take only one token at a time, and then it will generate the output and then go for the next word, and then you need to generate the text, and each new token becomes part of the input for the next step. So whatever the output it got, it this is the input for uh, present word to predict the next word. Suppose here the input I have taken is I love. What it should predict means learning. Based on these two words, it has to predict the learning, third word. And then we also have we have I love learning. So what it should do means based on these three tokens, it need to predict this because word. So this is called the auto-regressive generation. Means based on the previous words, to generate the future words like next words at a time by using the one token at a time. It should generate only one text at a time. This is called the auto-regressive generation. And how it will work means same as in encoder, it will take the input and it will tokenize it, and it will create the embeddings, and it will give the positional encoding also. So here in uh, encoder we have only two parts. Those are like multi-head attention and feed forward network. I will explain you it. uh, but we have a more in decoder. One is a masked multi-head attention, and then feed forward network. So it has a three components: masked multi-head attention, feed forward neural network, and the residual layer normalization. So first, masked self-attention. What is this masked self-attention means? GPT is not allowed to see future tokens. As I said, it will have to take previous words only. It should not allowed to see the future words, like future tokens. Why? Why means if it could see the future words, then what is the use of this training? So the main goal is it has to use the previous words and it has to produce the next token word. So for example, here I am learning the transformers. When predicting the learning, when predicting this word, it has to use just I am. So to it should not see the transformers. This is enforced using a casual marks. Here also we are taking these query key values exactly the same attention, but here uh, masked here. Same here we are calculating these weights, weight matrices. So how GPT understand this context? Suppose it does not understand the human language like humans. So as a humans, how we the text it cannot understand. So that's why it will understand this by using this attention. It understand the statistical patterns. So here each token looks at all previous tokens and assigns some relevant scores and build some context. And then it will generate the next output. So how token relevance affects the output? So here example prompt, the capital of France is, so based on these high relevances. So France has a high relevance, very high relevance, and then capital has high relevance. So that only, so here what we are doing, we get to know the capital of France. So France is the main important part. And then what is France? What we need to do? We know that we should know to the capital. So this is a high relevance, this is a very high relevance. So that we can get to know the next token, like what is the capital of this France is Paris. So if the attention focuses on the wrong tokens, it will give us the output as the incorrect ones. So first part is completed, and this is a multi-head attention. As I said before, multi-head attention means uh, focusing on different things at the same time here, like focusing on the grammar, entities, long range dependencies, instruction following. And this is a pre-training objective means, so giving the training data here. So why we are using this GPT as a in decoder? What is the use of it? Means it will trained on the massive data. It will deep transformer. It has some deep transformer layers. It has a long context window and strong attention patterns. And then GPT learns these languages, facts, reasoning patterns, code structures also. So what it will do means generating loop, like how it will generate the output means user will give that prompt, and that prompt should be uh, like the tokens are embedded, and then attention is applied, and then next token is predicted, token embedded, and then repeated till it continues until the end token and the max length. So GPT does not always choose the highest probability token. It has some techniques like greedy, top K, top P, temperature. So how this controls means by using this creativity and randomness. So this is all about the transformer architecture like encoder and decoder. So in simple words, what it will do here is it will take an input and then embeddings will happen, and then positional means we can give the order to each token, and then multi-head attention means uh, doing many things at a time at the same time, and then feed forward network like how at first it will have a self attention, like each word will look at the other words by using how the self attention work here is by using this query key value we can get to know the attention value, and then we'll get to know the final attention value here, and then we'll compare the query with the all the keys, and we'll get to know the what is highest weight to our related question, and then we'll get to know the final output. And then this is a feed forward network. So what is this means? Whenever we have completed the attention function, it passes each word through a small neural networks here. So what happens here is it will improve as the representation. So the encoder is about representing the input, right? So it improves the representation, and also it will use the same network for all the words. So how the flow will be means uh, first attention output, and then it should need forwarded to FFN like feed forward network, and then have a better understanding also. And then what happens here is, and then it adds the uh, adds a normalization. This is for stability, like to prevent from the vanishing gradients, and this is for stability we have using this. So this is a linear softmax means if we use the linear it is used it is used to produce as the vocabulary meanings like vocabulary sizes, and then we are converting it into the softmax here, converting all the scores into the probabilities, like words with highest probability will be chosen, right? So this is how it will work. And then decoder only means the same. It will take the uh, like a sentence. It will do the embeddings, and then it will add the positional encoding, and then uh, it has a three blocks like masked multi-head attention. Like the key role for this is decoder must not see the future words, and then we'll have a this is a multi-head attention as I said before only here. So this will happen. So from this it will get the multi-head attention, and then it will use the feed forward network same as encoder. It improves the representation here, and then it will assign the it will apply to each position, and then we'll have a linear layer like same as I said before. It will converts the vectors to the vocabulary size, and then it will convert the scores into the possibilities, so we can have a output probabilities like which word has the highest probability that will be chosen now. And this is so the model predicts the next words by using these linear and softmaxes. And so this will repeat at the six times, like n times. Here it has given as an n times. Usually it uses the six times. So the decoder also, decoder layers is also repeated n times. It helps the like in each layer it will have a deep understanding. And then the transformer first, it converts all the inputs into the embeddings and adds positional encoding. By using this input processing, it is using self attention and feed forward layers to create the context aware presentations. So same in the decoder, it uses the previous output, applies the mask self attention, and then attends to the encoder outputs, and then it predicts the next word by using the softmax. So this is how the transformer architecture will work. So we have discussed what is a transformer, what is the use of the transformer, why we are using this transformer. So what is a transformer architecture? What there in architecture, like encoder, decoder, what is an encoder, what is a decoder architecture, what happens in encoder, and then what happens in decoder. So this is the transformer architecture. Thank you.